Presentation in Unit 5. This is entitled Swim, Bike, Run. It says the only place that success comes before work is in the dictionary, and that's a famous quote by Vince Lombardi. The learning goals for this particular presentation are that you be able to identify the factors necessary for physical work to occur, distinguish between work and power, and use the appropriate formulas. In addition to that, we're going to discuss several of the different types of energy that you will see later in this unit and also in subsequent units throughout the year. So what we already know that energy is defined as the ability to do work. Now we've known that for several years because that was taught in middle school, but we also know that energy is conserved. So the energy that you get has to come from somewhere. So when you see something like an energy drink, the energy that you get comes from the stuff that's in the drink. So there's sugar and sorts of things like that that allow you to do certain things. Now, what we learn in the lab is that students that exert a greater force do more work. Okay, the amount of work you do depends on how much force you apply. In addition to that, those who apply the same force over a greater distance do more work. So we know that work depends on two factors, force and distance. We also know that the one who has the most power does not necessarily have to do the most work. Those aren't always related. Instead, the person who has the greatest power does the greatest amount of work in a certain amount of time. And that's the key thing because power is a rate. So energy. Energy exists in many different forms, but the key to energy is that it is always conserved in a system. So if you have a system that is closed off from everything else, energy is always the same. If you have 100 energy, no matter what you do to this system, it's got to have an energy of 100. Now you can reapportion that energy. You can have 99 heat and 1 kinetic energy, or you can have 1 heat and 99 kinetic energy. But no matter what you do, those things have to add up to the original 100. So there's several different types of common energy that you see. You see chemical potential energy. That's the energy that's stored in bonds. If you took chemistry, you would realize that whenever you have things that are bonded together, this right here represents the chemical potential energy. So the energy that's stored between two things that are connected. We also have gravitational potential energy. We're going to star that one because that's a key one for this particular unit. That's the energy that's stored due to its position relative to the Earth. So if you have a rock and you put that rock on the ground, there's very little energy stored due to its position. However, if that rock is above the Earth, there's a large amount of energy stored due to its location relative to the Earth. If you were to release this rock, nothing would happen. It doesn't go anywhere because it doesn't have energy because of its position. But if you were to release this rock right here, it would fall to the ground because it has energy relative to its position whenever it relates to Earth. Next, it says we have nuclear. Nuclear is the energy that's released in the combination or splitting of nuclei. So you probably talked about this in chemistry. You have a nucleus in the center of the atom. If you can take that atom and you can split it, that's what we call fission. And fission is a type of nuclear energy. If you take two nuclei and you slam them together really hard and it creates a bigger nucleus, that's fusion. And that is also something that releases energy. So that's nuclear. The combination has to do with the nuclei. Radiant energy, we're going to study later this year, is energy transmitted by electromagnetic waves. Now we're going to cover an entire unit on radiant energy. It's called the electromagnetic spectrum. Heat is also something that we'll study later in this year, and heat or thermal energy is the transfer of energy between objects of different temperature. So for example, if you have a 400 degree object and a 0 degree object, heat will transfer between these two things, trying to equilibrate the energy, and we will talk about that more later this year. Now, some of the other common types of energy that we're looking at specifically for this unit is kinetic energy. Kinetic energy is the energy of movement. In order for an object to have kinetic energy, it must be moving. If you have something that is perfectly still, it does not have kinetic energy. Kinetic, the word itself, kinetic, means to move. Okay? Work is considered to be the action energy. So it's what applies the force. So if you pull back on a rubber band, that's considered to be work because you're applying a force on something. If you let that rubber band go, it's also going to have a force as it snaps back. Now you also have elastic potential energy. Elastic energy is the potential energy due to stretch or compression. So once again, when you see a rubber band, that's an example of elastic energy. Many people don't realize this, but whenever you have atoms that are connected together, those atoms actually move back and forth relative to one another. Well, when they do that, they have some elastic energy. So the first example we have, it says describe the transfer of energy from the sun to sugar in a plant. So we're going to go back to biology here. We're going to say if we start out at the sun, the reason why the sun has energy is because it occurs in a nuclear reaction. Okay, so we have nuclear energy to begin with. Now, this nuclear energy can't make it all the way over here to Earth. So instead, that energy is transferred or converted into sunlight. Now, sunlight itself is not a type of energy. Instead, what we would call that is we would call it radiant. So now we have radiant energy, and that radiant energy is the sunlight. Now, when this radiant energy hits the leaves of a plant, that plant will actually take that and change it into glucose. Well, glucose is chemical potential energy. So you see how we can track the energy all the way from its original origin in the sun to radiant and then to chemical potential energy in a plant. The next one, it says describe the transfer of energy as a box is picked up off the ground and set on a table. So we have a table and we have a box right here. And when we pick up the box, we are applying a force. Okay, so whenever we apply this force, we have work. But before we do anything, where did we get the energy to do that work? Well, it came from some sort of food or some sort of drink or something that you had before that which gave you the energy to do the work. So we're going to say that this is chemical potential. So the chemical potential in your body is converted to work. That work is then transferred into gravitational potential energy. I'm going to say it's GPE because now the box has energy relative to its position on Earth. In other words, if released, it would fall back down. The next example we have says describe the energy transfer as a car initially moving down the highway slams on the brakes. Now, if an object is initially moving, we can say that it has kinetic energy. Now, if it has kinetic energy and it slams on the brakes, when it slams on the brakes, it's going to come to a stop. If it's going to come to a stop, it's no longer going to have kinetic energy, but that energy must go somewhere. So what happens is when you press on the brake, there are some things that lock up. Whenever they lock up, there is work done. In other words, there's some sort of force being applied to slow the car down. Once you have the work is then transferred into heat. If you were ever to get out of your car and go touch the brake pads, they're very, very, very hot after you come to a stop because they're stopping due to friction. Next, power versus work. The most powerful isn't always the biggest, it isn't always the strongest, it isn't always the fastest. It's the combination of those that makes the difference. Work, physical work, is the action energy that relates kinematics to dynamics. What that means is it's the thing that whenever you relate force and dynamics, one of the key aspects to physical work is it requires both force and movement. This guy right here is technically not doing any work. The reason why he's not doing any work is this boulder right here is not moving. If something is not moving, there is no work that's being done because work requires both. So it says, does a person leaning against the wall do work? Well, not unless the wall moves, which is more than likely not the case. So we have the equation here, and this is the way you'll see it on the formula chart. It says work is equal to force times distance. Now, more often, this is really displacement. Okay? It's really displacement, but remember, displacement and distance are the exact same thing so long as there is no change in direction. So, as long as there is no change in directions, you can think of it as distance. So the equation that we have, all energies are measured in joules. Okay, we're already familiar with force, we're already familiar with distance and displacement. So let's go ahead and see what some examples look like. The first one says, calculate the force exerted on a box when it requires 500 joules to move the 10 kilogram box a total of 25 meters. Now remember, the first thing that you want to look at is you want to look for what am I trying to solve for and what information do I know. So the first thing I'm going to do is I'm going to do my given. I have 500 joules, 10 kilograms, and 25 meters. Based on the fact that I know the units, I can say that the work is 500 joules because it matches with the unit. I know the mass is 25 kilograms because it matches with the unit. 10 kilograms. And I know that the distance is 25 meters. I know that I'm trying to solve for the force. So I'm trying to solve for the force. Force is question mark. The equation that I have that relates these things together is work equals force times distance or displacement. Now if you look, I have force, or I'm trying to solve for force. I have work and I have distance or displacement. But the one thing that I have here, and actually makes no sense to me, is the mass. The mass is nowhere in this equation. In fact, this right here is extra information that I don't need to know at this point. So I just kind of crossed it out just for now to let me know that it's not relevant to what I'm doing. Now I plug in the equation. 500 is equal to F times 25. Divide both sides by 25, and when you do that, it'll cancel out here, and then you'll do 500 divided by 25 on the other side, and that'll end up giving you a force of 20 newtons. Next, it says determine the work done on a 1,000 kilogram car by its engine if it accelerates at 5 meters per second squared for 25 meters. So once again, we know we have a 1,000 kilogram car, we know we have an acceleration, and we know we have a distance. So I can say mass equals 1,000 kilograms. Acceleration equals 5 meters per second squared. Distance is equal to 25 meters, and I am trying to solve for the work. Work is equal to question mark. Now I know the equation that relates these things together is work is equal to force times distance. The problem is that I don't actually have the force. So you may get stuck here and say, I don't know what I'm supposed to do. But you have to look at the variables you have and say, is there any way with what I have to make this work? Well, if you look, I have the distance, so that's good. So if there was only some way to find the force, then I can calculate the work. So what equations do I have for force? And you have to rack your brain and go, oh yeah, I have one for force. That's force equals to mass times acceleration, which is Newton's law, or Newton's second law. So what I can do is I can actually solve for the force and then plug it in, or I can do what's called a substitution. You can take this value for mass times acceleration and you can plug it in. And you will get work is equal to mass times acceleration times distance. You can then plug it in and you know you've got an equation for work makes you mad, or work equals mad. So now you can plug in. You can say work is equal to 1,000 times 5 times 25. When you put this in your calculator, you would end up with a rather large number of work is equal to 125,000 joules. Next, it says determine the work exerted on an object if it's subjected to the forces below for 10 meters. So this is a little bit of recall information. Remember, we're trying to solve for work. So I'm going to say work equals question mark. I know that in order to find work, I need to know the force and I need to know the displacement. Well, the displacement I'm given is 10 meters. So if I can find the force, which is in fact the net force, we kind of didn't cover that before, but it's the net force, we can go ahead and solve for the work. Now, if you're trying to find the net force, you would know that 50 cancels with 50. You would know that you have 100 and then you have 20 on the opposite side. So this net force right here is actually 80. You can use the equation work is equal to FD, or 80 times 10. When you do that, you get a work of 800 joules. In this lab, early in the lab and earlier in this presentation, that the biggest isn't always, or excuse me, the biggest or the most powerful is not always the biggest, the fastest, or the strongest. Instead, it's the one that's the most, is the best combination of all those. So here we have the equation for power. Power is equal to the work over time. Power is a rate. Now, a lot of us like to think of the electricity company as the power company, but really what they're not providing you with power, they're actually providing you with a type of energy or work. It's in the electrical form, but they're providing you with electrical energy. They're not providing you with power. Now, power is a rate, which means it's the energy divided by the time. So we're already familiar with work, we're already familiar with time. Power is the new one. Now, power can be a little bit confusing. Here's the reason why power can be confusing. Power, the variable is P, and it's got a number with it, like 100, and the unit is W. So the fact that this W is here, sometimes people get it confused with the variable W. But there's a difference between the unit and the variable. So we have an example. It says determine the time required for a 60-watt light bulb to give off 50,000 joules of energy. So I have this number and I have this number. Based on the fact of what they are, I can say P, power, is 60 watts. I can say W, which is my energy in this case, is 50,000 joules. I know that I'm trying to solve for time. Time is equal to question mark. The equation that I have that relates these variables together is power is equal to work over time, and I can plug my variables in. I can say 60 is equal to 50,000 over T. Now at this point you should realize that T is on the denominator and it can't be there. So I'm going to multiply both sides by T, and when I do that I get 60T is equal to 50,000. But remember, you're not looking for 60T, so you're going to divide both sides by 60. When you do that, you get T is equal to 50,000 divided by 60, which in this case is about 833 seconds. So you can see that a 60-watt light bulb can go through 50,000 joules of energy very quickly. So it's a good thing that you're not going to be billed on joules of energy. Instead, you're billed on a much bigger unit of energy called a kilowatt hour. Now, how much force is exerted by a 1200 watt engine that lifts an object 5 meters in 2.4 seconds? So we go ahead and look and see what we're looking for. We're looking for the force, so we say force is equal to question mark. It's an awful question mark. Okay, we know that the power is equal to 1200 watts because we know the unit for power is watts. We know that whenever you have 5 meters, that represents a distance. And we also know that we have a time of 2.4 seconds. So we kind of run into a little bit of a problem here because the equation that we have for power is equal to work over time. And if you look, you don't actually have work. So I've got to say, okay, well, I've got time and I've got power, so force isn't even in the equation. But I do know that work has another equation that goes with it. Work is equal to force times distance. So what I can do is I can get a new equation. Power is equal to force times distance divided by time. If you look, you have 1200 watts of power. You can solve for the force because you have a distance of 5 and you have a time of 2.4. So with all these variables in here, you would need to solve mathematically. So you've got 5 divided by 2.4, so you can multiply both sides by 2.4 over 5, and when you do that, you end up with a force of about 580 newtons. Last, we have what is the power of a weightlifter who lifts a 200 kilogram barbell 1.2 meters above their head if they're 1.7 meters tall and they complete the lift in 0.5 seconds. So we've got kind of an issue going on here. The first thing we want to do is let's go ahead and say we're trying to find the power. So we write P equals question mark. Now I do know the equation with power is equal to work over time. So now let's define the variables that are given to us. We're given mass, 200 kilograms. We're given two distances. We're going to have to look at that in just a second. And we're given the time of 0.75 seconds. So if we were to look at it, it says that the weightlifter has the 200 kilogram barbell 1.2 meters above their head, and the weightlifter is 1.7 meters tall. So we're going to assume he lifted it from the ground up a total distance of 2.9 meters because he lifted it 1.7 meters tall and then another 1.2 meters above that. So we're going to say that the distance that this barbell traveled was 2.9 meters. Now if you look, I'm trying to solve for the power. I have the time and that's great, but I don't have the work. So what I can do is I can do my substitution. I can say that power is equal to force times distance over time. You say, okay, well, there's a problem with that. Although I do have distance, that's getting me a little bit closer because I've got distance and I've got time, I still don't have the force. So I still can't calculate the power. And so I can say, okay, well, I have an equation for force. So I can change that into power is equal to mass times acceleration times distance over time. And at this point, you say, okay, well, I've got mass and I've got distance and I've got time. If only I had acceleration. In fact, you do have acceleration. Remember, you were lifting this object up against gravity. So when you're lifting it up against gravity, you can say that the acceleration is 9.8 meters per second squared. So you can say the power is equal to mad over time, or 200 times 9.8 times 2.9 divided by 0.75. The weightlifter in this particular example is exerting about 7,600 watts of power.